Hello, I'm Hans Doctor, the founder and CEO of Gradle. In this demo, I'm going to show you how you can use the developer productivity engineering techniques embedded in Gradle Enterprise to continuously improve with developer productivity metrics, KPIs, and trends, reduce the time to troubleshoot, build, test, and CI failures, minimize flaky tests and other avoidable build and test failures, speed up build and test times for Maven and the Gradle build tool by up to 90%, and reduce your CI costs and improve CI efficiency. All of this will dramatically increase your developer productivity while minimizing cost, release cycles, and frustration levels. Some of our customers have more than 200,000 Maven or Gradle build executions a day. Most medium to large engineering teams will have at least thousands of them a day, automating everything from building, testing, releasing, source and documentation generation, and dependency management. And just like with your apps, you need the data and tools to actively manage performance and reliability. Otherwise, even with the best build systems, your local and CI builds will become slow, unreliable, and troubleshooting build and test failures will be incredibly expensive and painful. This is a huge source of developer frustration, and for most of you, a multi-million-dollar developer productivity problem, right under your nose, if only you had the tools to act on it. Gradle Enterprise is a self-hosted service that collects comprehensive data of every Maven and Gradle build run in your organization, locally or on CI. It comes with a remote cache to avoid running build actions, including tests, unnecessarily, and also offers distributed test execution for faster local and CI builds. Maven users don't have to migrate their builds to the Gradle build tool to get the benefits from Gradle Enterprise. Let's start with the demo. With Gradle Enterprise, for the first time, you can get quick answers to some fundamental questions. What you're seeing here is the trend dashboard. In the overview, it shows us the number of build executions for the last 28 days, the cumulative time it took to execute them. There are additional metrics. Build time is the average build execution time. Serial execution time is for measuring how good your parallelism is. Avoidance savings are the average time savings per build you're getting from build caching and up-to-date checking. Build cache overhead measures the average time to download and unpack build cache artifacts. And finally, the average dependency download time per build. You can filter this by certain projects, for CI builds from a particular branch, for CI builds of a particular type, for local builds with changes that were not committed to version control yet, or for a particular user. Let's look at my builds over the last 7 days. As you can see, I'm not running many builds nowadays, unfortunately. Compare this to Yantrick, who spent almost half a day per week waiting for local builds to finish. If both of us submitted support issues for our builds, which one would you prioritize? Once you have those numbers, you can do some interesting calculations. For example, what is the overall amount of time developers are waiting for a local build or pull request build to finish? And what is the cost of that? Let's say you're doing 10,000 local builds per week with a 5-minute average build and test time. Multiply this by 52 weeks, and you can see that your developers have to wait a total of 25 engineering years per year for those builds and tests to finish. Let's say the fully loaded engineering cost is $1 per minute. It is often much higher. That's an equivalent to $2.6 million per year in wasted R&D investment. So shaving off a minute of that build time would give you back 5 engineering years or an additional R&D budget of $520,000 just by reducing wait time for local builds. And your developers will be happier because they're more productive. You will have faster CI builds, less context switching, and obviously you will also ship your software faster. Gradle Enterprise allows you to quantify the impact of many of your developer productivity vectors and thus helps you to prioritize where to invest in improvements and where not, and how to measure success. Even better, it will also help you in many ways to actually achieve those improvements, for example, by immediately making your builds and tests faster and improving their reliability. Another interesting metric to look at is the failure rate for your build and test executions. People often underestimate that number. If we look at the Gradle project, you see that over the last 7 days we had 1,320 local builds, of which 635 failed, a failure rate of 48%. For CI builds, we see typically failure rates of 20%. Such failure rates are fine. They come with the territory of changing the code and creating new features. If you have failure rates much lower than that, I would actually be concerned about your test coverage or your development activity. At the same time, with so many failures, if it is inefficient to debug them, it will negatively impact your developer productivity. Builds fail for 2 reasons, either because something is wrong with the build or the test, or because something is wrong with the code that is built or tested. Gradle Enterprise makes debugging in both cases more efficient. I just got a message from Jen that her local build failed with an exception that doesn't make sense to her. She also mentions that she gets a similar exception several times a month. Sometimes she is blocked by this for hours. At one point things will start working again, but she doesn't understand why. With Gradle Enterprise, this is now easy to report and investigate. Nothing needs to be reproduced, as the data of every build is captured in what we call a build scan. Jen just needs to send the build scan URL, then I can look at the build scan to figure out the root cause of the problem, without needing to reproduce the problem. Before build scans, Jen would probably not even have bothered to report such an issue. Let's look at the failure view. We have an artifact not found exception for example dependency 6.2.2. Let's try to understand what brings this dependency in by searching for it. We can see here that this is a dynamic dependency, similar to what are snapshot dependencies in Maven. That means the build always looks for the latest available 6.2 dependency. In this case, this is 6.2.2. The dependency detail view reveals the binary repository where the dependency is looked up from. Let's check our binary repository to see what is going on there. In the 6.2.2 folder, we see that there is a POM file, but no jar file. That is why 6.2.2 is detected, but cannot be downloaded. After I deleted the corrupt 6.2.2 directory, I pinged Jen, telling her that the problem is fixed and asking her to try again and to send me another build scan. A few minutes later, Jen responds that everything is working now. I check her latest build scan and can see that now version 6.2.1 is picked up. I want to make Jen aware of this, so I copy a link that directly takes you to the dependency detail view and share the link with her. Finishing the support request took us just a few minutes instead of hours or days. Developers and CI pipelines are unplugged quickly. People responsible for build or CI spend their time on new features instead of inefficient troubleshooting. As you will see later, Gradle Enterprise also enables you to proactively find build and test failures and failure patterns without requiring developers to even file an issue. We still don't know why the 6.2.2 dependency folder was corrupt in the previous example. We will investigate that later. A very common debugging problem for developers is that everything was working at a certain point in time and then it didn't work at a later point. And you wonder what has changed that might have caused this. For example, here we have a failed Jenkins CI job. It provides a link to the Gradle Enterprise build scan. If we go to the build scan, it allows us to compare this build with the previous build that was successful. In this case, the comparison tells us that the failing build is using a different version of a dependency. Example dependency 6.2.2 versus 6.2.1. Try to figure this out without such a comparison feature. Good luck. In other cases, the comparison might show you differences in the environment, like a difference in the versions of Java being used or the number of cores. and if the comparison tells me that nothing has changed along such dimensions, I can fully focus on other potential reasons for the failure. Reducing debugging dimensions quickly is at the heart of efficient debugging and key to reducing the mean time to repair a failure. There are many troubleshooting incidents that could be avoided altogether by detecting and fixing failures early. In a previous example, we helped Jen to fix a build failure caused by a missing dependency. Wouldn't it be cool to learn if other people and builds are affected by the same problem? Let's go to the failure dashboard. The failure we ran into is listed here. Its failure details tells us that it occurred 148 times over the last 22 days. So our previous fix seems to have helped only temporarily. We learn that not just Jen is affected by it, but also other people who never reported it, like Luke and Eric. We can also see that the failure occurs on local machines as well as on CI. If the one occurrence Jen reported to me had been the only one, I would probably not bother investigating further. Knowing now that it affects all environments and many users shows me that this is a real productivity killer that should have been fixed weeks ago. Knowing the environments in which it occurs also helps to understand the root cause faster. The regular frequency of the occurrence, every 7 days, is also a valuable data point for root cause analysis. The build scans for all those failing builds are listed here. All those builds fail because the 6.2.2 version of the library is unavailable in a binary repository. When I look at a build scan for this project from a day where this failure did not occur, like on November 20th, we can see that version 6.2.1 is always used. So I can conclude that every 7 days, for some reason, a 6.2.2 Maven POM file is published with no jar file. And it turned out that there was a legacy project where the CI build ran only every 7 days to execute some smoke tests against the current environment. While running, it accidentally published a corrupt library module, which always broke many builds until someone manually deleted the corrupt directory in the binary repository. Nobody knew why this happened. Nobody knew that it affected many people from being productive. We were able to figure out the root cause and fix it. This will not happen anymore. Let's talk about test failures. We're looking here at a project where test suites have been broken for months. No one is fixing those tests anymore, and that results in even more tests starting to fail. If you would look at the test report for a single build, you don't know where to start fixing the tests. The failed tests could be flaky tests, broken tests, or healthy tests that detected a real bug in your code under test. Let's see how the test failure dashboard can help us here. The first thing we're trying to understand is which tests are completely broken. They're usually easier to fix than flaky tests. We can see that there is an obvious list of test cases that fail most frequently. Let's look at browser test. We can see here when it started to fail constantly. You can also see the individual test methods and their behavior. Here's performance test, which started to be broken a little bit later. We ask our developers to fix both of them. Let's extend the time period of the dashboard to include the week after this was fixed. You can see that there are less test failures. You can also see that the browser test case is no longer broken. Neither is the performance test case. Let's talk about flaky tests. Flaky tests are non-deterministic tests. Gradle Enterprise detects flakiness by rerunning failed tests within the same build execution. When failed tests succeed after retrying, we classify them as flaky. Flaky tests are not the only unreliable tests. Some tests are deterministic, but they have failure clusters at certain time periods because of certain environmental conditions. For example, because services are down. The test failure analytics that we have shown previously can help you to identify those. One thing I cannot emphasize enough is that rerunning failed tests is a good detection mechanism for flakiness, but a terrible remedy. First, tests can be flaky because the test logic is flaky, but a test can also be flaky because the code under test is flaky. By rerunning them until they succeed, without fixing them, you ship flaky behavior to your users and customers. Second, if you don't fix flakiness, flakiness will accumulate. This increases the build and test time and wastes valuable compute resources. Finally, a flaky test can fail with a probability of 1% or 99%, so relying on retries to address the problem still results in a growing number of builds that fail because of flaky tests. Now that I got this off my chest, let's do something about flakiness. Here you can see the test dashboard with flaky test detection enabled. By being able to identify the flaky tests and their impact and fix the most impactful ones first, we can get them under control. On the test failure dashboard, I can identify end-to-end test as the worst flaky test. It is flaky more than 40% of the time. I can look at the details of this test to learn which test methods are responsible for this. Now that this test was identified, our developers prioritized fixing it. In the meantime, I discovered something else. When I filtered for local builds, I learned that developers are not running end-to-end test locally at all. And here we can see why. They're running local builds, but everyone is excluding the end-to-end test when running tests. This is one of many examples where Gradle Enterprise not just helps you to optimize your toolchain, but it also gives you insights about organizational behavior and how the toolchain is used. Okay, our developers told me that end-to-end test has been fixed. Let's look at the data 1 week later. We can see that the flakiness is gone. When we filter just for local builds, we can also see that the developers are no longer excluding this test. This once useless test and annoying piece of code is now a valuable addition to our local NCI quality gate. After fixing many of the flaky tests, we can see that the overall number of test failures has actually increased. Is that a bad thing? Not at all. It means that our automated tests are used more frequently and are now doing a better job to find real problems in our code under test. Did we get rid of all the flaky tests? There's still some, and there will always be. Like you're never done vacuuming, you will never be done fixing flaky tests. And some tests have so little flakiness that you might be okay to live with it for that particular test. Gradle Enterprise enables you to make such nuanced decisions. The test dashboard also connects you with the build scans. When we look at the details of a particular test method, it provides a list of build scans for those cases where the build has failed or flaky tests. The build scan itself also tells you that a test was flaky, which is useful when you're troubleshooting an individual build failure. Let's talk about accelerating build and test time. An important component of that is build caching. For those who have not heard about build caching or are not exactly sure what it's about, let me explain the concept. When you run a single build, it usually means you run at least hundreds of build actions, like compiling a particular module or testing it. A build cache caches the output of a single build action. When another build is executed on the same machine or different machine, if the inputs have not changed, build actions can use the cached output of a previous run of the same build action, instead of executing again. Examples of those shared outputs are compiled classes, test results, check style reports, or generated source code. A build cache makes building a single source repository faster. This is very different and complementary to a dependency cache like Artifactory or Nexus, where libraries that represent other source repositories are cached. Let's see this in action. I have checked out the Apache SLF4j project. It is a small project with 12,000 lines of Java code, and it is built with Maven. Let's run the build and tests. On the left, using the build cache, and on the right, without the cache. The build using the cache is now finished. Let's look at the build scan. You can see that it took Maven 13 seconds to execute 152 build actions. 54 of those were retrieved from the cache. The build not using the cache is still running. It's a good example for waiting time caused by build executions. It's finished now. The build scan tells us that it took 38 seconds to execute the same 152 goals, with 0 of them being retrieved from the cache. We have a difference of 38 seconds to 13 seconds, which is a reduction by 65%. Keep in mind that this build has not been optimized yet for best cacheability. Those results is what we're getting right out of the box. One of our customers, LinkedIn, runs hundreds of thousands of builds every day. They wrote a blog post about the benefits they're getting from the build cache. Here's a chart showing the performance improvements. It is important to understand that you can improve the initial savings you get from caching significantly by optimizing the configuration of your build and also by improving the modularization of your code base. Gradle Enterprise provides build caching for both Maven and Gradle builds. It also comes with tools to monitor, optimize, troubleshoot, and administer the cache infrastructure and the cache effectiveness. Let's use a real-world project to get some real numbers. Many of you are using the SpringBoot project. The SpringBoot team is a user of Gradle Enterprise, and they allowed us to use their real-world data for demonstration purposes, which is awesome, and I want to say thank you to the SpringBoot team. What I will show in the next and final demos is a little bit more in depth than the previous examples. I hope you will enjoy. Let's go to the trend dashboard and look at their CI builds. I want to explain a little bit the metrics on this page so that we can later better understand the impact of the build cache for the SpringBoot project. Build time is a simple metric. It is the wall clock time between the start and finish of a build. Next is the serial execution time. This is the sum of the execution time of all build actions. To understand this a little bit better, let's go to the timeline of a single build from the SpringBoot project. Every rectangle here represents a build action. The serial execution time is the sum of the lengths of all those rectangles across all the rows, whereas the build time is the length of a single row. Those white spaces in between the rectangles are, for example, caused by build actions having to wait for the output of other build actions. The more white spaces you have and the less rows you have, the closer the serial execution time is to the build time. The minimum for the serial execution time is the build time, and the maximum is the build time multiplied with the number of processes, in this case 4 times the build time. The ratio between serial time and build time measures how much faster your build time is because of parallelism. The SpringBoot build is an average 2.6 times faster out of a theoretical maximum of 4. This is pretty good utilization. If they allocated, let's say, 12 processes to this build, 2.6 would mean it is a significant underutilization of the provided compute resources. Now we have all the context to reason about the next number, which is called avoidance savings. This is basically the execution time savings you get from caching. Now, fasten your seatbelts. The average execution time savings for every single CI build is 1 hour and 19 minutes. I repeat, 1 hour and 19 minutes for each and every build over the last 19 days. This is serial time, so in terms of the actual build time, build caching is making the CI build faster by roughly 1 hour and 19 minutes divided by 2.6, which is 30 minutes. So without the cache, the average build time would be 45 minutes instead of 15 minutes. Not bad. But you're not just saving 30 minutes of build time, you're also saving 1 hour and 19 minutes of compute resources. Resource effectiveness is another huge benefit of a build cache. For teams with smaller projects, of course, the absolute time savings will be lower. With the SLF4J project in the previous example, caching decreased the build time by only 26 seconds, from 39 seconds to 13 seconds. But if the same number of developers is working on multiple smaller projects, the absolute number of builds is higher. So you have to take this into account when you're trying to reason about the impact of a build cache. Build scans provide you with a detailed breakdown of the caching activities per build. Here is the Gradle Enterprise Performance Dashboard for the SpringBoot build. This dashboard allows us to identify individual builds according to their value of certain performance properties, like builds with long build times or builds with long dependency download times. Each column represents a single build. The length of the column represents the time value of this build for the selected property. Right now, this is the build time. Let's select the remote build cache property to identify builds with a high number for time savings from the remote caching. Let's pick a build with a high number. We can look at the details of this build. It tells us that the cache has provided execution time savings of 2 hours and 31 minutes for this build. Let's go to the build cache page of this build's build scan. You can find here details about the configuration of the local and the remote caches, for example, which particular remote cache node was used. You also find cache usage information. You can see here that 780 build actions didn't need to be executed because of the cache. Let's look at the cache overhead. It took 5 seconds to download the output of the build actions from the remote cache. This is serial time. The network speed during the download was 10 megabits per second. As you can see, we don't necessarily need a massive bandwidth to benefit from the cache. Whatever your situation is, Gradle Enterprise will give you the insights to reason quantitatively and precisely about the effectiveness of caching in your different environments. For example, different office locations, CI, and people working from home. You get the caching insights even at build action level. Here is a build scan from the Gradle open source project. This is a local build that someone ran from their home. We have a task here called Patch Kotlin Compiler Embeddable, that is patching the Kotlin compiler. So the output of the task is the Kotlin compiler itself. The patching job is computational intensive, but the task is also I/O heavy because of the large output. Tasks that are mostly I/O based, like typical copy or archive tasks, usually don't make sense to cache, and Gradle would by default not cache them. On the other end of the spectrum are tasks that are very computational intensive with relatively small outputs like tests. This is where the gains from caching are the highest. So should we cache this patch task or not? Well, we need more insights to make that decision, and Gradle Enterprise gives us that. We can see here that retrieving the task from the cache took 17 seconds. We can also see that this is 10 seconds longer than building it locally. With that information, you can now make the decision to disable caching just for this task in low bandwidth environments like those, after confirming that this is typical behavior. With a faster network, this would be different. Getting it from the cache would be at least as fast as building it locally, and you're saving compute resources and paying for that with a higher load for network and disk I/O, which is often cheaper. Finally, every cached build action provides you with a link to the build that has produced the cached output. So you have a full audit trail for where your build results are coming from. Gradle Enterprise collects metadata about the inputs of every Gradle task and Maven goal that is executed. Examples for such inputs are source files or class paths. Having this metadata allows Gradle Enterprise, for example, to show you which inputs have changed between two build runs. One reason why you might want to know this is to analyze the reproducibility of your build. Another reason is to understand why you are not getting cache hits, although you are expecting them. Here, we compare the inputs of two builds. The second one was executed right after the first, and nothing was changed in between. Yet we see that for 4 tasks, the inputs have changed. For this example, I'm only interested in the cacheable tasks, so I filter for them. That leaves us with the test task. We see that the class path of the test task has changed. Diving in further, we see that there is a file with the name timestamp properties in a class path that has changed, and I can also see the full path of that file. Aha! This is an auto-generated file that changes with every build execution and, as a result, always changes the input of the test task, which causes a different cache key to be calculated, and we never get a cache hit for this task. With that information, we can now reconfigure our Maven or Gradle builds to ignore this file when calculating the cache key for the test task. So when you do initial experiments with the cache and don't see good results immediately, those kind of issues are often behind that, and they can be usually fixed easily once detected. For optimizing network latency and availability, you can set up multiple cache nodes. You can define replication between them. You have settings for storage control, access control, and event logging. You have monitoring for the health of the nodes. You can look up individual cache entries, see in which nodes they are stored, download and inspect them, or purge them. Gradle Enterprise also provides usage metrics like hit rates, data transfer, and cache storage. The economic benefits of a build cache are extremely compelling in terms of increased developer productivity and compute resource savings. Even for smaller builds or builds that are considered fast, those savings are significant. As important, we see everywhere a strong relationship between build time and how early and how often developers are running builds for feedback. Early and frequent feedback is a critical success factor for teams that want to go agile. Build caching also discourages bad behaviors like breaking up your code base into more source repositories than necessary just to make the builds faster. And to top things off, it takes a lot of compute load from a developer machine. In sum, build caching is a no-brainer for most teams. Tests are an essential part of any professional software development process. One of the biggest problems with tests is that executing them often takes a long time. We've checked out the Apache Cassandra project. We will now run the 1064 tests of the 84 test classes under the org Apache Cassandra CQL3 package. Here the tests are executed in a single process on a local machine. Long-running tests affect individual developer productivity because of long wait times and context switching, team efficiency because of fewer pull requests being merged per day, and the quality of your product because tests are run less frequently. The build has finished. Let's look at the build scan. It took 23 minutes and 33 seconds to execute the 1064 tests. With Gradle and Maven, you can execute tests in parallel. Here the tests are executed with 4 local processes. This is already noticeably faster. However, the maximum number of parallel forks is limited by the machine's CPU and memory resources. And if you use too many of those, the developer machine might be unusable for other development activity while the tests are running. The build has finished. Running the test took 12 minutes and 11 seconds. Nice. Let's bring this to another level. With Gradle Enterprise's distributed testing, you can scale beyond the limitations of a single machine and distribute the execution of tests to as many local and remote processes as you want. Here the tests are executed with 4 local and 12 remote processes. Each process is represented by a Gradle Enterprise test agent. While the tests are running, Gradle Enterprise provides a live view of what is happening on each agent, for example, which test it executes, or other activities like uploading sources and class paths. Tests can define agent requirements and will be only run on agents that match those requirements. For example, a certain version of Java or certain operating system. To evenly distribute the load between the agents, historical data about test execution time is used to decide which and how many test classes are sent to each agent. The build has finished. Running the tests took 2 minutes and 15 seconds. With distributed testing, we could speed up test execution by a factor of 10 compared to executing with a single process, and by a factor of 5 compared to local parallel execution. You can apply hundreds of agents. The distributed testing engine is optimized to keep the overhead of distributing tests low. For optimal fine-grained distribution, you might have to sometimes reorganize in which test class the test method should live. When running the tests with 32 agents, out of the box the test execution time is 2 minutes, which is not much faster than with 16 agents. Why? The unit of distribution are test classes. The minimum achievable execution time is the time it takes to execute the longest running test class. If you look at the build scan, we can see that the tests of some test classes take more than 90 seconds. On top, you have the setup and tear down costs for the test class, so we cannot optimally balance the load. After moving some of the test methods to other test classes, we got the execution time down to 1 minute and 9 seconds. Test results are automatically aggregated from all the agents to the machine running the build for things like coverage reports. While we have shown only local builds in this demo, CI builds will get the same benefits from distributed testing. Distributed testing is available for users of the Gradle build tool. Maven support is coming soon. I want to talk a bit about CI efficiency and CI cost. LinkedIn is saving 800 hours a day of CI resources because of build caching, and that number is growing. For Elastic, just the money they saved from the cache for their CI agents running on Google Cloud Platform was more than what they had to pay for Gradle Enterprise. This is not just about caching. Wherever we go, we see build actions and tests being executed unnecessarily, or often twice. Build parallelization is not optimized, and build actions operate ineffectively. How could it be any different? Without the insights to monitor and profile, which is what Gradle Enterprise enables you to do, and which not just makes the build faster, but also reduces CI cost. We discussed in detail how to proactively manage and minimize avoidable build and test failures. We discussed how those failures affect developer productivity. Every build that fails because of environmental issues is also wasting CI resources, and Gradle Enterprise helps you to reduce this waste. This is also about quality of service. This chart from one of our customers shows you the percentage of CI builds per day that could not be executed right away but had to wait for a CI agent to become available. The timeline shows before and after the build cache was introduced and optimized. They went from 40 to 50% of the CI builds being initially in a wait queue to none. Before wrapping up, I want to make a few points about deployment. Gradle Enterprise sets up quickly as a self-hosted service and scales reliably to the largest builds on the planet. Gradle Enterprise also provides an export and streaming API for all its data to integrate with other systems like BI tools or monitoring solutions. In closing, developer productivity engineering is a practice that acknowledges the fact that you are wasting tremendous amounts of resources without a dedicated, continuous effort on making builds, tests, and CI not just faster, but easier to fix, more reliable, and more efficient. To recap what we said at the beginning, with Gradle Enterprise for the first time, you now have the tools, data, and insights to continuously improve with developer productivity metrics, KPIs, and trends, reduce the time to debug build, test, and CI failures, minimize flaky tests and other avoidable build and test failures, accelerate build and test times for Maven and the Gradle build tool by up to 90%, and reduce your CI costs and improve CI efficiency. All of this adds up to providing a great developer experience. There's no better way to do that than to give them back 1 day per week in lost productivity, as was experienced by our customers SAP and Tableau. Now developers can focus their energy and skills much more on their passion, writing great code, and not on frustrating, uncreative stuff like waiting a long time for builds and tests to complete or troubleshooting failures inefficiently. While at the same time, your team saves millions of dollars in R&D costs and delivers real competitive advantage to your company. Many of the world's leading technology-driven brands have found Gradle Enterprise to be a game changer. We hope you are inspired now to learn more about Gradle Enterprise, because we believe you will also find it to be a game changer and a no-brainer.